Unmute. Audio options. Is it working? Ah, it looks like it's working. Okay, you should be able to hear me. Oh my, 5 people. Good, good. Everyone's right on time. Well, all right. Let me start with a bit of administrative stuff. I think there are enough people here. You may be able to answer this all-important question. I am going to be at a cyber competition next Friday. Let's see what we got here. Good, you can hear fine. Thank you, KT. Good. So if you can hear, I realized I'm not going to be able to do this next week at this time, so we need to move this to some other date, and I wondered if we could do it on Tuesday, Halloween, at night. If people have any comments, let me know. You can send a chat message or something. Is anybody available at 6 p.m. on Tuesday? I'm just guessing that's a good time. All right, here's a comment. Tuesday is fine with Haifeng. Good. Anybody else have a comment? I will be involved in trick or treat. Well, yes, that's an issue. Not good for me. All right. I can't do Wednesday. I don't really want to skip a week because we started late and we won't finish. I can only do any other day of the week at some other time than 6 p.m. Do people want to meet even later? That would get pretty late for people on the East Coast. Is there anybody that could meet earlier, like 4 p.m.? 4 p.m. California time, which I guess would be 7 on the East Coast. KT can, okay. And someone's okay with 11, okay. 4 p.m. later is also fine. Well, you know, something else just occurred to me. I'm going to be in Rochester. There's an event at 5 p.m. I can probably just do it as usual because that stuff will probably all be over by 9 p.m. The time zone change will probably mean I can participate in the event. So, you know, let's just leave it the way it is. I just realized because of the time zones, I can probably get out there by 9 p.m. Eastern Coast. So let's leave next week the way it is. I'll adjust this page to remove this statement. And never mind, it's just me being confused. All right. So never mind about that. And I guess we can proceed with the usual stuff. And if anybody has any questions, just use the chat. That seems to be working pretty well. So we're up to 4A here. All right. And that should be coming up. There it is. All right, good. So this is security engineering, part 1. And here, let me just minimize some windows to try to clean up my screen. All right, there. I don't know if that stuff is in your way, but it's kind of in my way. All right. So this is all in part 1. The main new information here, I think, is security models. That was new information to the CISSP when I did it, although I see it now migrating into Security Plus. And then a lot of the rest of this is actually basic hardware stuff. Anyway, so the security models are what led to the current ideas about security. These are the mathematical computer science models that led to the current confidentiality, integrity, and availability analysis, as far as I can tell. And there's a bunch of them, but the main ones are Bell-LaPadula, Biba, and Clarke-Wilson. Those are the ones that really helped us understand what security is. And so here's the idea. We just call this up and down. If you think in terms of a mandatory access control infrastructure, unclassified is the lowest, top secret is the highest, you call it going up if you're going into a more secret level of classification, and down if you're going the other way. So the simple security property is no read up, which is kind of obvious. If you are only cleared for secret information, you are not allowed to read anything higher than secret level. And that is the Bell-LaPadula model. It's missing an L here. So that's the whole point, of course. If you have a low security clearance, you're not allowed to read high security clearance objects, and that protects confidentiality. Now, you could talk about writing up, and the Bell-LaPadula model did not prevent writing up. For example, something could be at a secret level, and it could then be written up and go to a higher level. And that does not violate confidentiality. It does, however, violate integrity of top secret objects. And the other part of the Bell-LaPadula model was no write down. You cannot take top secret data and write it at a lower level, because that would obviously be declassifying it. And you would not let someone just do that with a write operation. They would have to go through a formal process of declassification. All right. Read down is, of course, okay. People with high clearance should be allowed to read low clearance documents. That doesn't do any harm to the confidentiality, which is the only consideration of this model. All right. So the mathematical models of these systems are called state machines. You have a set of objects and a set of users and whatever you have, documents, computer systems, and so on, and they're in some state where people can, one subject can use this object and one subject can use that object, and the mathematics is considering all the possible states and perhaps considering transitions between the states and showing that they all still obey your security model. So the Bell-LaPadula model was the first one for the Department of Defense, and the only thing they worried about here was confidentiality. So they had no read up and no write down. So a low security person could not read any higher level data, and a high security person could not divulge any high privilege data by writing it down. That was the idea. So this maintains confidentiality, but it does not protect integrity. A low security clearance person can submit false data, which goes up to high clearance levels. And that is an issue here. There is a tranquility property available, which says that security labels don't change while the model is operating. And there's another property you can talk about, weak tranquility, where security labels can change, but only in a way that does not conflict with security properties. That's a minor detail in the system. Another system is lattice-based access controls, where you have various levels of clearance. Clearance need to know classifications, and subjects have an upper bound, least upper bound, and a greatest lower bound of access. This is another model. I don't hear it used that often, but it has this lattice of objects and these various types of permission called alpha, beta, and gamma. Anyway, but the main one is the Bell-LaPadula model. That's a simple one that provides confidentiality but does not provide integrity. And the BIBA model is the opposite. You just flip both rules, no read down and no write up. So this creates integrity. The objects at the top cannot be altered by anybody at a lower security clearance, and the people at the top do not read anything lower. So the way I remember these, the Bell-LaPadula model is like the Department of, is like the espionage agencies. The KGB did this. Since everything is so secret all the time, they don't even know what they're doing, and they don't really stay on mission. There was a KGB team that broke into a U.S. government office to steal something, and another KGB team had already stolen it, but the secrecy meant they couldn't talk to each other and they didn't know what was happening. And the BIBA model is more like the Roman Catholic Church, where you have this holy document at the top, the Bible, and nobody can, at any level, can write to it, but everyone can read it. There are no secrets, and the idea is everybody should stay on mission because everybody can read the top document that cannot be changed. Anyway, that's integrity. The fundamental high clearance object cannot be modified, and everybody can read it, but in order to have the maximum integrity, you have to have no confidentiality. All right, and that's the game here. It turns out, of course, both of these models are far too extreme for any reasonable situation, and what you have to settle for is something in the middle. You would like to protect integrity and confidentiality to some extent, and therefore you have to accept some degree of failure of both of them. And that's what the Clarke-Wilson model does, which is something like a Microsoft domain controller. You have objects and you have subjects accessing them, and you can make a matrix of permissions that suits your business need. So the primary concepts here are well-formed transactions and separation of duties. The well-formed transactions are the motions from one state to another, and so you have unconstrained data items that come in, things like user input that do not necessarily fit in your security model, and then you have some process to bring them into the system, giving them some permissions. And then you have constrained data items, which are data that is now inside the system and now must maintain its integrity. And you have a transaction procedure that will verify integrity and move things around and leave an audit record. Separation of duties is a common security concept for defense in depth at many levels, where if you have some important activity, you make sure that two people have to be involved in this activity. One person does it, another person reviews it in some way, so that they cannot have one person committing fraud. You would need a conspiracy of two people to commit fraud, and that's more difficult. All right, so I got a few cahoots about that stuff. Let's bring them up here. If I can get my stuff out of the way. I cannot minimize Zoom while I'm recording a meeting. Well, I can shove it to the side anyway. Okay, Kahoot. There we are. Log in. And my Kahoots. Okay. Oh my goodness. I forgot to upload the Kahoots. Well, that will degrade this thing a bit. All right, what we'll do is we'll go on for another section or two, and then we'll have a break, and I'll put them up. I've got them written. I forgot to put them in the system. So, but I know it makes people more awake, so we will do it. We'll just do them a little bit out of order. Onward we go. All right, so information flow is another method that focuses on the motion of data in the system. All right, Bell LaPadula and Biba are in this type of model. There's a Chinese wall model, which is used, what's intended for financial consultants and banks, and lawyers use it too. This is how you can handle having two related cases at the same law firm. There is a wall of information separating what people are allowed to share from one group to the other to avoid conflicts of interest. Non-interference is a desirable property of a security system that has multiple levels of security, so that if you have objects at a high security level, they will not have any effect on objects at a low security level. This is very difficult to achieve in any real system. If it fails, then there's a covert channel in the sense that people can measure something at a low security clearance and deduce something about high security clearance activities. And I don't think I got the example here, but it's coming up later. One thing I've been told by military people is that foreign military agents can tell when the United States is going to engage in a major military operation by watching the pizza consumption at the Pentagon, because everyone makes their staff stay late and they all order pizza. So when there's a lot of pizza ordered, there's a major military move being planned. And that's an example of a failure of non-interference. Some secret thing is happening, and it has consequences that are not treated as secret. It's very difficult to avoid that. Another one is side channel attacks, like measuring the power consumption of a computer. You can deduce something about the cryptographic key. All right. Then there's a take grant system where you have take, grant, create, and remove, which are rules, and you have a complex graph of these relationships. So it looks like this. Alice can create and remove privileges to this secret documents folder so she can grant privileges to Carol, and Bob can take her privileges. So people have various abilities to modify permissions here in this model. And you have an access control matrix, which looks again like a Microsoft domain controller. People have access to a file or access to an application, and they have, each person can have a different level of access to these objects. And there's something called the Zachman framework for enterprise architecture, where this is intended to suit a business. So you have all these roles in the business on the left, and you have all these objects and business activities across the top, and you define rules getting to all these things. Then there's the Graham-Denning model, where you have subjects, objects, and rules, and you can now have activities here like destroy object, create object, grant access, and so on, and you specify who's allowed to do these things to various objects. And there's an HRU model, which is similar and just has a similar group of operations. I know this reminds me of the Linux permission structure, which is read, write, and execute, but the Microsoft permission structure is just different language and a different mixture of it all. Things like list folder, execute program, full control, read only, and so on. All right. So there are modes of operation for things in a mandatory access control environment like the military. If you're going to have classifications like secret and top secret and classified, then you're going to label the people, the data, and the computers. And now you have an issue of how many computers you take and what is it that separates a high security level from a low security level. And these are 4 ways to do it. The dedicated system is the simplest and the oldest procedure. You must have an air gap between all security levels. And I've been told by military people this might mean you have 7 computers on your desk, because you have to have 1 for top secret and 1 for secret and 1 for classified and 1 for unclassified, and there may be other categories involved too. This is the simplest way to do it. All information stored and processed on that system has to be at that security level or lower. And nobody's allowed to touch the device unless they have their appropriate clearance. That's one way to do it. Another way to do it is system high, where there are multiple labels on the document, but you make sure that all subjects using it are cleared up to the highest object. So you, again, do not have to trust the operating system or the hardware to really separate these levels. Compartmented is where each subject accessing the system has clearance, but they don't necessarily have access approval or need to know. So you have technical controls doing the horizontal side. Remember, we talked about this before. Vertical controls are the security levels from classified, unclassified to classified, to secret to top secret, and horizontal controls are need to know. And here you let the software do the horizontal control, but not the vertical control. And of course, the last option is multi-level, where you put objects of multiple sensitivity labels on the same system, and you let subjects of different security levels use the system, and you trust the software to keep everything organized. This is what really happens in Microsoft Windows domains. Everybody can use every computer, and you trust the system to identify who you are and give you the right amount of access. And this is done in terms of a reference monitor. It's a term we'll see later that they have to meet the Orange Book specifications. There has to be a thing called a reference monitor running in the software, which identifies who everybody is and makes sure that only the people with top secret clearances are allowed to see the top secret objects. All right. So there are formal bodies that certify these things. And here's some of the examples. The TC-SEC is the famous one from the 1980s. This is the Orange Book, which specifies what computer systems are secure enough for U.S. military use in many levels. Then there are international models that were developed later. This is it, the Orange Book. There was a series of books called the Rainbow books here with many different colors covering different military standards. And this one was the one that handled computer systems. So it rates you from A to D. And here's how it is. A is the highest level of security, and D is the lowest level of security. D is minimal protection. This would be something like a Windows 95 or an MS-DOS machine where you have no security at all. You may remember Windows 95 and in Windows 98, you didn't even have to log in. You could just close the login box and get in without a password. There were no permissions on the disk at all, like a floppy disk. You could read and write any file on the disk at any time, and there was no way to even attach permissions to the file. It was just, if you had physical access to the object, you had total control of everything on that object. No protection at all. Level C is more like a home computer where you have what's called discretionary access control. Every object is owned by somebody, and they can do whatever they want at their discretion. Let's see, I got a chat message. Let's see what's up here. Show slides. Something, I think you moved. Wait, you can't see? No notes showing? We need the PowerPoint. Uh-oh, I hope it has been that way all along. Well, let me see if I can figure out what happened here. Exit full screen. Something went in full screen. Have you not been seeing slides all along? My beautiful system appears to be fouling up today. Is it better now? Let's see. Let me bring back the chat. I cannot minimize. Okay. Somehow I've got somebody's camera. Okay, I can go down here. Ah, here we are. And now, somewhere I should see the chat. All right. And, all right. I'm just trying to see. Okay, I still have my people, and I have no comments. Hopefully, no slides since Kahoot IT. My goodness. Well, all right. I tell you what. Let's take a 10-minute break. I'm going to stop the share and come back, get some of the Kahoots up, and we'll see if I can get things organized here. I think my remote communication is not working too well, so I'll start it again in 10 minutes and see if we can get back on track here. All right.